In our last video, we discussed alpha decay, where heavy nuclei eject a large number of protons and neutrons in the form of a helium nucleus in order to reduce the nucleus size and for the atom to become more stable. We're going to look at two different types of what is called beta decay in this video, and this is a little bit different than what we saw in the previous video. This time we are still seeing nuclei change from one type of element into another, but doing so in kind of a bizarre way. For beta decay, what we're looking for are what we call neutron-rich nuclei. What I mean by that, the truth is, most heavy elements have many more neutrons than they do protons. However, there's a balance, and it's possible for a nucleus to be unstable because it has essentially too many neutrons. And so that type of nucleus might undergo beta decay. And the way that that happens, we can think of very simply as this: a neutron, which we know to be neutral and about the same mass as a proton, does the following. The neutron essentially becomes a proton and an electron. If you think about it, that's very possible, at least from a theoretical perspective. Protons have about the same mass as a neutron. Electrons have almost no mass. Protons are positively charged and electrons are negatively charged. If you add those two together, they balance off to form a neutral charge, which is what we see in neutrons. So the idea is simple. If a neutron turns into a proton and an electron, and it emits or spits out that electron, then essentially what we see is a nucleus that now has a lower ratio between neutrons and protons, and that will cause the nucleus to be a bit more stable. So let's take our example in this particular problem. We have 53 protons according to our atomic number, and we have 78 neutrons if I take the difference between my mass number and my atomic number. If one of those neutrons in the nucleus turns into a proton and an electron, then the atomic number is going to increase by 1, but the mass number will stay the same, because while we are gaining a proton, we're losing a neutron, so the mass number does not change. In effect, what happens is the electron is ejected from the nucleus. And in order to keep this a balanced nuclear equation, again, as we talked about in a previous video, we'll write the charge of the electron here and the mass of the electron here. Electrons have essentially no mass compared to protons and neutrons, and their charge is negative. If I look at the left side, I have 53 and 131. Right side, I have 54 and -1 for a total of 53, 131 and 0 for a total of 131. And I've produced a new element in the process. The daughter isotope is xenon. And the ratio, while it doesn't change much, the ratio between protons and neutrons is lowered. So again, we look for this to happen in neutron-rich nuclei. Let's take a look at a problem. Let's look at carbon 614, carbon 14. Carbon 14 has a total of 6 protons and it has 8 neutrons. What we're saying here is maybe that ratio of 8 to 6 is a little bit too much in favor of the neutrons. And so the nucleus will eject an electron by having a neutron turn into a proton and an electron. And so when we do that, again, our atomic number increases by 1, but our mass number stays the same. You look that up on the periodic table, that's going to give us nitrogen, 14. And in addition, we get an electron, which is known as the beta particle. Should have probably said that earlier. The electron is what gives this type of decay its name. And in particular, this is called beta negative emission, and it's the most common form of beta emission, or a beta ejection, if you will. We're going to look at a secondary type where the opposite scenario is in play. This is called beta positive decay, or a name I prefer, it's called positron emission. This is a type of decay that happens in proton-rich nuclei, where maybe you have too many protons compared to your number of neutrons. That being said, let me remind you that in almost all nuclei, the neutrons are going to outnumber the protons, except in very light elements. So what goes on here? Well, essentially the opposite of what we saw in beta negative decay. What we think of happening in positron emission is a proton turns into two particles, a neutron and what we call a positron. Now, you may never have heard of a positron, but you can think of a positron as being in all ways the opposite of an electron. So it actually has all of the characteristics of an electron, except that it is positive in charge. It's actually a type of it's something we call antimatter. So in this case, here's what we see happen. Let's say we've got a parent isotope. Potassium has 19 protons, it has 21 neutrons, but perhaps that's too many protons to make that nucleus stable. And so what we see happen again is a proton turns into a neutron. That's going to drop the value, or it's going to drop our atomic number by 1. But again, since we pick up a neutron while losing a proton, the mass number does not change. We do have a new element as our daughter isotope. It's argon now, and we produce a positron. This is our beta plus particle. And again, it is just like an electron, but with a positive 1 charge. So let's try one for ourselves. If we look at 10, 10 is, we're looking at 10, 116. It's got, I guess, 50 protons and let's count them, 66 neutrons. But we're saying we have too many protons in this particular case. And so a proton changes into a neutron and a positron. That decreases our atomic number by 1. I believe that is the element indium, and our mass number stays the same. In order to achieve that, we have to have balance, and so we show the ejected positron also on this right side. And again, this is what we would call our beta positive particle. Okay, great. We'll see you next time, everybody.